Hello everyone, this is the demo video of our Computer Organization Lab course project which required us to develop a simulator for assembly code. Here we present MIPSploration.asm, a web-based simulator for MIPS assembly code. It supports 32 registers, 4 kilobytes of memory, pipelining with and without forwarding, 2 levels of cache with customizable settings, and this list of assembly instructions. The simulator can be instantly launched at the link shown here given in our GitHub repository. We decided to go for a web application using the React framework so that it would be very easy for anyone to get started without any hassle or cumbersome setup steps. We have used a clean, clutter-free interface with a modern dark aesthetic that makes it inviting, especially for beginners. The project was developed in 3 phases throughout the course of the semester. The overall layout of the simulator consists of the integrated editor, the console and space to display pipeline visualizations, the left side panel which displays registers, the memory segment, cache tables and cache settings. We also have a sliding help panel with sample programs and instructions that illustrate how to use the simulator using well-labeled diagrams. In the first phase, we set up the integrated code editor, registers, memory and console. You can enter your MIPS assembly code here, or you can also upload a .asm file from your computer using the upload functionality. You can use the step button to execute the assembly code line by line. Observe how the instruction which is pointed to by the next PC or program counter is highlighted in the editor. The registers and memory show the step-by-step changes. The registers are highlighted when their values change. A special detail is that the registers and memory values can be viewed in decimal, hexadecimal, or binary. You can click on Run to execute the entire program. The console prints out the integers during system calls or syscalls that print out values to the screen. For each phase, we first came up with multiple test cases that cover all possible situations. We then proceeded to the design and implementation for it. In phase 2, we implemented the pipeline display such that it shows the instructions in the pipeline in an easy to visualize manner. The MIPS pipeline we have implemented has 5 stages: instruction fetch, instruction decode register fetch, execute, memory, and write back stage. The 2 types of forwarding allowed are EXE-MEM to IDRF-EXE and MEM-WB to IDRF-EXE. We display both pipeline diagrams with and without forwarding, which can be viewed by switching these panels. These tables are carefully generated by parsing through each instruction, identifying dependencies and latencies for various stages. The diagram shows which instruction is in which stage of the pipeline for every clock cycle. The stalls are clearly demarcated. We also display the number of cycles, the number of stalls, and the IPC or the instructions per cycle. Moving on to phase 3, we implemented and integrated 2 levels of cache to go with the existing setup. You can select various cache settings such as cache size, block size, associativity, and latency for both the L1 and L2 cache using the elegant GUI features. The caches use a non-inclusive and write-through design paradigm because they are simple to implement without much overhead for multiple additional checks. You can also select the main memory latency, which is the time taken for an access to the main memory. The cache tables shown here are updated in real time and can be observed during a step run. The cache tables show 1 block per row. Adjacent sets are demarcated using different colors. Each block in the cache table represents 4 bytes or 1 integer. Since the simulator only supports integer operations, the entire memory system of the simulator is designed for integers of 4 bytes. Notice that the pipeline diagram shows the appropriate number of memory cycles depending on the latency of the corresponding memory levels and also shows the resulting stalls. One of the main bottlenecks in performance in processors is due to memory. To put this into perspective, we have created a special feature called the hypothetical ideal case. If this box is checked, we show what the performance would have been if all the memory accesses took only one cycle. Notice the IPC before and after. The significant increase in IPC shows that improving memory is a major motivation for achieving better performance. The carefully selected sample programs cover all possible corner cases that we could come up with while testing our pipeline and cache implementation. The simulator also successfully runs bubble sort, which is available as a sample program in the help section. We developed an in-depth understanding of MIPS architecture during the course of the project, and we enjoyed coming up with our own simulator. We hope that beginners in computer organization will find MIPSploration.asm useful and exciting. Thank you for listening to this demo.